The question says define conductivity and molar conductivity for the solution of an electrolyte. Also discuss their variation with concentration. Let's take a look. First of all, if you're trying to measure conductivity of any solution, how exactly are you going to determine that? Well, by passing current through a solution. And if you're trying to pass current through a solution, how exactly you would be able to pass a current through a solution? Well, it is usually done in very specific equipments. Okay, and we have a cell or an apparatus for measuring this conductance. How is it? It's usually made in the form of a cube. Well, a cube or even a cuboid for that matter is okay. This is the way, right? It could be very well a cuboid, no issues. There is some area of cross section here. Yes. Same area is on the side, of course. Yes. And there is some separation L, length L, in between these two parallel opposite phases of the cuboid. Of course, yes. Now what do? I fill up this cuboid with the solution for whom I have intentions of making conductometric measurements. I fill up this. Fine. What else? And then this side and this side both are connected to some kind of a cell. We pass current. And as we try to pass current by various methods, we could actually make measurements. For example, by using Wheatstone's bridge, we could make measurements of what is the resistance of this solution. You remember in physics, we talked about resistance, yes? And we said that this resistance R is directly proportional to length of conductor. And in this case, it will be the distance between these parallel plates L. And it is inversely proportional. By experiment we can find it is inversely proportional to area of cross section, and this is in this case the area of cross section. So we say R is equal to rho L by A. This is what physics people used to say. In chemistry, we just take 1 by rho is 1 by R L by A. R is resistance, so reciprocal of R is defined as G, which is conductance. L by A is called, of course, cell constant, and 1 by rho is denoted by a Greek letter kappa, and kappa is called specific conductance or conductivity. So what is conductivity? We have just managed to derive also, although this was not asked, but just to explain you, I just needed an excuse to make an explanation because students usually find this tough. It's very, very easy. Kappa is GL by A. How do we in words define this? We say conductivity of a solution is defined as conductance of a solution. It is defined as conductance of a solution placed in a conductometric cell having unit area of cross section, having unit means 1, having unit area of cross section separated by a unit distance. So let me repeat, what is conductivity kappa? Conductivity is defined as the conductance, G is conductance, so it is the conductance of a solution which is placed between two parallel plates having area of cross section unity separated by unit distance. That's it. And of course, what are the units? We must write down units also. Units of kappa are Simon per meter or Simon per centimeter, or Simon is per ohm per meter or per ohm per centimeter. Please remember, these are SI units, and since 1 Simon is 1 per ohm or 1 mho, these are identical units. Right? So this is about conductivity. What about molar conductivity, lambda m? What is that? That's also very simple. Molar conductivity, which is also denoted by lambda m, it is the conductivity of a solution. It is the conductivity of a solution which contains 1 mole of the electrolyte. Conductivity of a solution containing 1 mole of electrolyte when filled between parallel plates separated by unit distance. When filled between parallel plates separated by unit distance. Please note that in case of lambda m, area need not be unit area, of course, obviously. Why? Because you have to add enough solution so that it contains 1 mole of electrolyte. Right? What are the units? Units for lambda m are Simon meter square per mole or Simon centimeter square per mole. They look ugly, don't be bogged down by this. The simple expression. Is there a relation between kappa and lambda m? Yes, there is. Although this is not asked, but just let me mention, lambda m is kappa by c into 10 is to 3 if centimeter, CGS units are used. Okay. And in case SI units are used, instead of 10 is to plus 3, it becomes 10 is to minus 3. This is just a formula. If you have this, great. But again, this is not a part of this question, but we'll be using this very often, so I just happen to mention this. If you are just supposed to answer this question, I have answered this already. Last part. Discuss their variation with concentration. That is very simple. Let me say, as concentration increases, kappa increases. As concentration increases, you find conductivity increases because within the same solution you have more ions, so they can carry more current by common sense. But as concentration increases, you find lambda m decreases. Molar conductance decreases, yes. Molar conductance decreases, and there is an equation also which is called Kohlrausch law. Lambda m is lambda m naught minus b root c. Although this is not really very much a part of this question, but then the variation with concentration has been, it was discussed by Kirchhoff and later on it was refined also. Now this is more called Debye-Huckel-Onsager equation. Don't worry about names much if they sound very bad to you. Lambda m versus concentration, this is the way you write it down. Lambda m naught and b are constants. Concentration c is a variable and lambda m is a variable. So as you can see, concentration increases, lambda m decreases. This question talks about molar conductivity. What does it say? The conductivity of 0.2 molar solution of KCl at 298 Kelvin is 0.0248 Simon per centimeter. Calculate its molar conductivity. How do we do this? Well, it's just substitution and formulae. What is given? First, let's write down what is given to us. Given is C naught, concentration is concentration is 0.2 molar. Temperature 298 KCl is fine, least interested, it's usually the case. Kappa, the molar the conductivity or the specific conductance is 0.0248 Simon per centimeter, and lambda m is what is asked. How do you solve this? It's direct formula substitution. And how's that? That's simple. Solution. Lambda m is 10 raised to 3 kappa by c. In CGS units, if it is there in CGS units, this is the case. So what do? We just substitute. 10 raised to 3, what is kappa? Kappa is this is 248 into 10 raised to minus 4. Well, divided by 0.2, which gives you 124 Simon centimeter square per mole. Done? This is the value of molar conductance. And this question talks about, well, the very basic or simple idea or the definition of cell constant. It says, the resistance of a conductivity cell containing 10 to minus 3 molar KCl solution at 298 Kelvin. Let me just keep noting what is given. I am given KCl solution. I am given the concentration is 10 to minus 3 molar. And the resistance is found to be 1500 ohms. The resistance R is 1500 ohms. What is the cell constant? So what is asked is the cell constant, or what we call L by A. If the conductivity of this solution at 298 Kelvin, please check concentration is same. So the same solution they're talking about, and conductivity or the specific conductance is so much. So kappa is being given as 1.46 into 10 raised to minus 4 Simon per centimeter. Now you would say this is different. No, I've just shifted decimal by 1 unit. That's it. And this is what I get. Right? I'm given this, I'm supposed to find cell constant. How do I do this? It's a simple basic definition. I'll just motivate you to recall. Say if I take a conductivity cell, it's a cube and there are two parallel plates and these are separated by a distance L. They have cross-sectional area A. And if I pass current, there is solution filled up here in the entire cube. Then you would say resistance of the cell R is proportional to its length. It is inversely proportional to its cross-section area. So R is equal to rho L by A. This is what we say, right? And if we just shunt it, 1 by rho is 1 by R, L by A. L by A is called the cell constant. 1 by R is nothing but the conductance, and 1 by rho, rho is specific resistance, 1 by rho is specific conductance kappa. So 1 by rho by definition, we define this as kappa. Kappa, what is kappa? Kappa is a Greek letter and which is used to denote specific conductance. That's it, that's it. What do we do? Substitute. This is 1.46 into 10 raised to minus 4 is equal to 1 by R, 1 by 1500, L by A. Oh my God, do I not need concentration? I don't seem to be needing concentration at all, my dear. And what do I get? This is Simon per centimeter and 1 by 1500 ohms. Please remember, Simon is 1 upon ohm. So this actually cancels off. And what do I get? I get cell constant L by A. Is simply how much? It is 1500 into 1.46 into 10 raised to minus 4. Fancy. 1, 2, 3, 4. That is 0.15 into 1.46. How much is that? 15 6 are 90, 15 4 are 60, 69, and 15 are 15, 21. Oh my God, this is 0.219 per centimeter. Is that the answer? Yes, that's the answer. This question says, the conductivity of sodium chloride at 298 Kelvin has been determined at different concentrations and the results are given below. Fine. You have concentration in terms of moles per liter and you have kappa in Siemens per meter, but it's not just kappa, it is kappa multiplied by 100. So that the value looks good. Fine. This is the thing. Calculate lambda m for all concentrations and draw a plot between lambda m and root c. Find the value of lambda m naught. How do we do this? Let's begin. How do we begin? Well, let's recall the formula. Lambda m, molar conductance, is kappa into 10 raised to minus 3 by c. If the units are SI units or meter. Please remember, In case CGS system is used, we use 10 raised to minus, instead of 10 raised to minus 3, the formula shows 10 raised to plus 3. But nonetheless, we have meters, and Simon per meter, if you notice this. SI units, so we are using 10 raised to minus 3 in the formula. So using that, can I find lambda m for various concentrations? Yes. And I'm supposed to plot lambda m versus root C. Okay. So I would prepare one more table along with, like I'm already given a table, right? So along with, in parallel, I would need one more table calculating lambda m and root C. So kappa has to be multiplied by 10 raised to minus 3. So we already have 100 times kappa as this. Let's start. We'll substitute and calculate. So lambda m for the first case, how much would be lambda m? Lambda m is kappa, which is 1.237 into 10 raised to minus 3. Now, this is 100 kappa. So kappa actually this much into 10 raised to minus 2. 100 times kappa is 1.237. So kappa itself would be equal to 1.237 into 10 raised to minus 2. That multiplied by 10 raised to minus 3, oh my god, that is even worse. Divided by what? Concentration, which is 10 raised to minus 3. That wanes off. So I get kappa as 0.01237 Simon meter square per mole. And actually this is not the value of kappa. Kappa only this much. What we have calculated here is value of lambda m, which is how much? Kappa, this much is kappa multiplied by 10 raised to minus 3 upon C, and it is so much. Is it the first value? Yes. What about second, third, fourth? We'll win over each of them one by one. We have this now, we have to multiply it by 10 raised to minus 5. So once we take this value, now we don't have much space here. Can I do this up so that we have more space for the third entity? Fine. So that would be 11.85 into 10 raised to minus 5. Why minus 5? 10 raised to minus 2 from here and minus 3 from the formula, so that would make it 10 raised to minus 5 again. Divided by concentration. Concentration is 10 raised to minus 2. How much would that be? That is 11.85 into 10 raised to minus 3. Okay, and how much is that? 1, 2, 3. This is 12.37. This is 12.37 into 10 raised to minus 3. Units are same, Simon centimeter square per mole. This much. The third one, let's see what do we get? 23.15. 23.15 divided by 2 into 10 raised to minus 2. And this is 10 raised to minus 5. How much is this? Let's divide. This is 11 point, how much? 5, fine, and 15 to 7, 5 into 10 raised to minus 3. From 12.3, 11.8, 11.575, it seems to be reducing. The next one and the next one. It's a very routine calculation. So this is 55.53 into 10 raised to minus 5 divided by 0.05. Fine, that is 11.106 into 10 raised to minus 3. And the last one, 106.74 into 10 raised to minus 5 divided by 0.1. Oh my god, how much is that? That is this is 10.674 into 10 raised to minus 3. Units are same, Simon meter square per mole. These are the different values of lambda. In experiments 1, 2, 3, 4, 5, this is what we have calculated. And the instruction is plot them against root C. It's not just C. We are supposed to take a dirty square root of C. Let's do that. How much is root C? Let's see. Root C would be, if I take a square root of this, for convenience, let me take this as 10 into 10 raised to minus 4. So what I get is root 10 into 10 raised to minus 4. Root 10 is 3.16. So I have 3.16 into 10 raised to minus 2 molar to the power half. This is root C here. What about root C here? 0.01 10 to minus 2, this is 10 to minus 1. 100 into 10 to minus, sorry. This is simply 10 to minus 1, which is 10 into 10 to minus 2. This is root C. What about this? This is 20 into 10 to minus 2. So, no, 2 into 10, this is 2 into 10 to minus 2. If I take a square root, 1.414 into 10 to minus 1. This is root of 5, 2.23. Into 10 to minus 1. How much is that? Root of 10 into, this is 3.16 into 10 raised to minus 1. What I'm taking, I'm just doing root C, that's it. And this is very ugly. So I'll also convert this to 0.316, like this. So this is simply 10 raised to minus 1, 1 into 10 raised to minus 1. So 10 raised to minus 1 is common throughout. 0.316, 1, 1.414, 2.23 and 3.16. Root C is consistently increasing and we can see lambda m is consistently decreasing. So what do I get? I get, of course, if I plot lambda m versus root C, I would get a straight line going down. If I extrapolate this line, if I extend this line ting here, then at this point I get lambda m naught. That would be the value of lambda m naught, right? So one portion we have done, we have calculated all the lambda m's, root C, we have all data points, and the next step lies in actually plotting a proper graph. Let's do that. Now students, if you take a look at this, we have to plot lambda m versus root C. I'm going to use this opportunity to tell you some very beautiful facts about graph plotting also. It is not just this question. I'll be telling you in general a lot many ideas about how exactly to plot a good graph. Graph anybody can plot, but there are few points. Say for example, lambda m versus root C. Look at the values of lambda m. You have 12.37, 11.85, 11.58, 11.11, 10.67. So from 10.67 you get 11.37. There is some kind of a variation, but then the variation in data is in a very narrow range, between 2 units. From 10.67, if I add 2 also, I get 12.67 and the maximum value is 12.37, which is lesser only. If I just start the origin from 0, I would get a very flat graph, a very small kind of a line. A good graph is that which uses the entire graph paper. So please note, your origin need not start from 0. On y-axis, if I say I choose to start from, instead of 10.6, since the beginning point is 10.67, I could begin with 10.5. Oh wow, you're beginning with 10.5, why not 0? I could use 0, my dear, but if I use 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Say for example, I use, the 10 would be here and 12 would be here. So entire graph would be finished between this strip. This portion of my graph paper is a waste, this portion of my graph paper is a waste. So what is my aim? My aim is only to utilize my graph paper? No, the aim is to reduce error. The more expanded version of graph I make, the less is going to be the error, as you will see very shortly. So yes, we could use origin as 0, 0. But this is not the best thing in this case. I'm starting the origin from 10.5 for y-axis. For x-axis, 0.32, 1, 1.41 to 3. We could start with 0 also, because 0.32 and 1 such values are there. And how many spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 centimeters. Now, if I just plot this till, say this around 4, so then 1, 2, 3, 4, if I take this as 1, 1, 2, 3, 4, this as 2, 1, 2, 3, 4, this as 3, and 1, 2, 3, 4, this much as 4. Please note, I could have taken 1, 2, 3, 4 centimeters also like this. In that case, all I would have got is a very stupid graph like this. That's it. A simple ting, 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 4 points clustered together, and the rest of the graph paper is blank. You understand nothing. So I have used a scale in which I can utilize the entire paper and I can spread this over. Are you getting that? In the same fashion, when you look at lambda m, which scale I'm trying to use? From 10.5, I have intentions to go till 12.5. And this is, up till here, this is 20 centimeters. So if this is 20, to 10.5, I'll say this is 11.5, and I'll say this is 12.5. Oh my God. So I'm using the entire spectrum. So what is the scale? In this case, from 10.5 till 11.5, I'm just covering 1 unit. So 1 centimeter, there are 10 centimeters is 1 unit change. That means 1 centimeter on y-axis, 1 centimeter corresponds to how much? 0.1 into this 0.1 units. What are the units? These are 0.1. For 0.1 variation in lambda m, I'm going to use 1 centimeter. Beautiful. And for root c, as you can see, I'm using 4 centimeters for 1 unit. So 4 centimeters, 1 centimeter corresponds to 4 units. No, sorry, 4 centimeters correspond to 1 unit. Sorry for this ugly mess, but then this is the way it is. 4 centimeters. If you're confused, look here. I'm using 1, 2, 3, 4 centimeters, and this is only 1. So 1 unit of root c, I'm using 4 centimeters. Is it fine? Let us begin to plot. So 0.32. First, 1 looks good. I'll plot 1. So lambda m is 11.85. Now 11.5 is already here. Fine, I'm using pencil now. 11.5 is here. Then this would be 11.6, 11.7, 11.8. 11.85. Beautiful. I have this point. 11.85. Let me just to highlight that, let me use ink. I have located this. What did I do? See, every centimeter corresponded to 0.1 units. So 11.5, this is 11.5. 1 centimeter, 11.6. 1 more centimeter, 11.7. 1 more centimeter, 11.8. And then half a centimeter, 11.85. Very accurate. And that gives me the ability to plot decimals also very beautifully like this. I have plotted 1 point. Congratulations. What about 0.32? Now, since 1 unit is 4 centimeter, 0.32 units is 0.32 multiplied by 4. And how much would that be? 1.28. 1.28 centimeters. So 1.28 or 1.3 centimeters. So find 1.123 centimeters. I have got this. And how much up? This is 12.37. Lovely. Now 12.37. This is 11.5. Fine. Then 0.6, 0.7, 0.8, 0.9, 12. So this is 12. Yes. Then 12.1, 12.2, 12.3. Yes. And 7 up. The 12.37. I'm getting this line. This line is on this horizontal. I have 12.37. And on 1.3 centimeters. So I'll just take 1.3 centimeters here. 1. Observe very carefully. 1.3 centimeters. 1, 2, 3. This is the point. So 1.3 from x-axis on the x-axis and so much distance on y-axis. Yeah. Very beautifully, this is my point. So I've got this point, I've got this one. Similarly, let us plot the remaining ones also. Similarly, let us draw the remaining 3 points also, which I've got marked. And they, as you plot them, you might be horrified to discover that they don't really appear to be in a straight line. Oh, we have made an error. No, not really. See, we have plotted the experimental values. And now comes a very, very important point. You are supposed to draw a straight line through these points. Now, this might sound perfectly absurd. How can you draw a straight line when there is no straight line? This looks like a curve. And again, it looks like another curve. Now, when such a case is there, please understand we are supposed to get a straight line. So what will we do? We try to make a straight line which passes through as many points as possible in such a way that if you draw a line, a straight line, then if it doesn't pass through all the points, then the points which don't fall on it, half of them should be on one side and the other half should be on the other side. The deviation, the average deviation on this side and that side should be the same. So what do you mean we don't understand? See, it's like this. I'll just give you an example. Now see, for example, if I draw a straight line passing through these points. Now, is this a good drawing? No. Why? Because I will be getting 2 points exactly on one side of the line and no points would be on the other side. There are just 5 points. If I take these 3 roughly on my line, then this is not a good idea. Can I take, say, for example, if I take these 3, is this a good idea? This looks like a much better idea. Why? Because I've got 1 point on this side and just note 1 point on the inside and outside. Well, so shall I draw the line? Yes, definitely. Let me. I'll need to rotate this so that at least I can see this and draw the line for you. And as we do this, can you see that there is 1 point and the other point on 2 sides, and roughly the distance between them and them, this side and that side, is approximately the same. You could say that maybe if somebody else draws this, the person would have drawn a slightly different line. Yeah, very much possible. It could be very drastic also. Say, for example, if you draw something like this, this would look like these 3 points also are more or less collinear. If you draw a line like this, you get a very different slope. But then this is wrong. Why? Because the remaining 4 and 5, they are both on the same side, which indicates that this is not a good fit. So, whenever you are trying to fit a line in between, say, 5, 6, 7 points which are not collinear, please remember that line is considered more accurate, which is drawn in such a way that some points lie on one side while the other points lie on the other side. The perpendicular distances also should be roughly the same. So in this case, I guess we have a very good fit. Does this question possess a unique answer? No. Why? Because a slight variation in the exact answer may be there depending upon which line one chooses to make or fit. But now that we have it, can we see where exactly this graph is touching y-axis? Because at whichever place that y-axis is being touched, I get lambda naught m or molar conductance at infinite dilution. If you read this value, this comes out to be lambda naught m is 12.39 into 10 raised to minus 3 are the units which we have talked about. So for lambda naught m, this is the graph and that is the answers. Conductivity of 0.00241 molar acetic acid is some values given. Simon per centimeter. Calculate its molar conductivity. If lambda naught m for acetic acid is so much, what is the dissociation constant? There are 2 layers to this question. We are talking about weak electrolytes here, acetic acid. So first let's take up the first part which says, we are given conductivity is so much. So kappa has been given to me as 7.896 into 10 to minus 5 Simon per centimeter, right? Concentration C naught is 0.00241 molar. Fanciful. Now, what about lambda? So lambda is kappa into 10 raised to 3 upon C. If CGS units are present, I'll use that. This is 7.896 into 10 raised to minus 5 divided by 2.41 into 10 raised to minus 3. Right? Of course, this much into 10 raised to 3. This gives me my lambda. What is this? Molar conductivity. Lambda m, yeah. Molar conductivity would be simply by formula this much. Can we calculate this? Of course, we can do that. Not very pleasant calculation though, but we'll get there. Now, once we obtain certain value of lambda m, they are talking about the second. Lambda naught m is given as so much. What is the dissociation constant? So, this is the first part, and now let me do the second part, which says alpha. Degree of dissociation alpha is lambda m by lambda naught m. So, I can get degree of dissociation simply by this. How much would that be? That would be, well, I need this lovely calculation. Lambda m by 390.5 Simon centimeter square per mole. Yeah. So all I would need to do is just to substitute. Let's take a look. On calculation, lambda m comes out to be 32.76 Simon centimeter square per mole. Please, please, please don't you ever forget the units. You must mention the answer with units, otherwise your marks will be deducted. Your answer would be invalid actually. This is lambda m, right? And if I substitute here, 32.76 Simon centimeter square per mole. Well, this division does not look very pleasant. Had it been 39.05, the answer would have been 0.1. This is quite less than 0.1. If you calculate, this comes out to be 0.084. Wow, this is alpha? Yes. And how do I get degree of dissociation? No, alpha is gone. What is dissociation constant? Let me calculate that for you also. And this is the way it is. If HA dissociates as H plus plus A minus, initially if concentration is C naught, and if degree of dissociation is alpha, change is C naught alpha, C naught alpha, C naught alpha, then at equilibrium, what do I get? I get C naught 1 minus alpha, C naught alpha, C naught alpha. Fanciful. What is Ka? C naught alpha, C naught alpha by C naught 1 minus alpha, which is C naught alpha square by 1 minus alpha. And alpha I know is 0.084. Can I substitute that? Of course I can. And that would give me the value of Ka. Simple mathematical calculation, and that would give me the value of Ka. If I do that, Ka for acetic acid would come out to be 1.86 into 10 minus 5. There we are. Question number 12 is a very fundamental one. How much charge is required for the following reductions? 1 mole of Al3 plus to Al. Now, if you are reducing Al3 plus to Al, you need 3 moles of electron. 1 requires 3, so 1 mole requires 3 mole. 3 moles of electrons, 3 into 96500 coulombs. Please remember, 1 mole of electrons is called 1 Faraday charge. And 1 Faraday is, roughly it is rounded off to 96500 coulombs. Multiply that by 3 and there you get 0, 0, 3 Faraday is the 15th, 3 16, 19th. Oh my God. 2,89,500 coulombs, that is one enormous number. Yes. Or you could call it 3 Faraday charge. You may call it 3 Faraday or you may call it so many coulombs. Both are the correct answers, yes. What about this? 1 mole of copper, 2 plus to copper. Well, and what about permanganate? Permanganate plus something something gives you manganese ions. Now, do you see how much of the change? From plus 7, manganese is going to plus 2. If I balance this, I get 5 electrons like this. So, at one place, I have 2 and at one place, I have 5 electrons. What about charge? Charge Q will be 2 Faraday, 2 into 96500 coulombs, which is how much? 1,93,000 coulombs. Huge, huge, huge charge. And this is going to be even better, 5 Faraday. Q is 5 Faraday, which is 5 into, how much is that? Well, 96, this is 482,500 coulombs. That is enormous, 4,82,500 coulombs. This is like fourfold. Done? Done. Well, in this solution, please remember, I gave you an approximate value of 1 Faraday, which is roughly 96500 coulombs, but more accurately, 1 Faraday is 96, not 500, but 487 coulombs. There's a very small difference. Less than 0.1%, but still there is a difference. If you use a more accurate value of 1 Faraday, well, calculation is not difficult. You just have to multiply by 2, 3 or 5. But these are the numbers you get, which are very close to the numbers which I quoted, but these are more accurate answers. Oh, what do we do for NCERT? For board exams, these are the answers which would be expected. You will be not expected to approximate. Many of the students who take JEE coaching, NEET coaching are used to this approximation. So I just warn you, be more accurate. And if board exam asks you such a simple question, then they expect a more accurate answer like this. Done? Done. Now this is a question based on electrolysis. What does it say? How much electricity in terms of Faradays is required to produce what? First part is 20 grams of calcium from molten calcium chloride. If you have calcium chloride, that means you have calcium ions which you are trying to reduce to get calcium. If you want 20 grams of calcium, that means you have 20 upon 40, that is 0.5 moles of calcium. Okay. And as you can see from stoichiometry, 1 mole, you need 2 moles. So for 0.5, you need 0.5 into 2, that is 1 mole of electrons, which is 1 Faraday charge. Why? Because charge carried by 1 mole of electrons is 1 Faraday. That's it. Okay, that's that simple. Yes, it's that simple. But you did not use a formula. We don't need a formula. We can use simple stoichiometry for mole concept. But nobody want a formula. We are dying to use the formula. Let me give you the formula also, though I could use a method too. I have just solved this using basic common sense. But we can do it from method also using Faraday's law of electrolysis. Using the formula, in case you want to do this by a second method using blind formula, can we do that? Yes. And how's that? We'll use Faraday's first law of electrolysis. And what is that? What does that say? It says that mass of substance liberated or dissolved at an electrode W is MIT by NF. We have a formula. In our case, we have 20 grams of calcium. So 20 gram of calcium, its molar mass or atomic mass is 40. We know that. Into IT by N, 2F. Why 2F? Because N is equal to 2. There are 2 electrons being used. Fine. So what I get? I get IT by F is 20 into 2 by 40, which is 1. Which means IT is 1 Faraday. But IT is nothing but charge Q. So charge Q is 1 Faraday, or 1 Faraday of charge is needed. That's a very interesting and stupid way of doing it. But yes, if you are comforted by use of a blind formula, and there's nothing bad about it, you can do the second method also. Although the first method is simpler, more elegant and very beautiful. Now let me do the second one for you. It says 40 grams of aluminium from molten aluminium oxide. So you have Al2O3 and you're using electrons and you're making aluminium and O2. Let's forget about oxygen. We are taking aluminium. There are 2 aluminium atoms. Yes. And how many electrons? There would be 6 electrons. Actually, in fact, if I'm just writing half the reaction, I'll write 3 times oxide like this. This is only at cathode. O2 can undergo oxidation at anode, etc., etc. We are not interested. So this is the way we can write. Aluminium ions are being reduced to aluminium. Oxide ions are simply released in the solution. I need 6 electrons for that. So if you're planning to get 40 grams of aluminium, fine. 40 grams correspond to 40 by 27 moles because atomic mass of aluminium is 27. And 2 moles give you 6 moles. So 40 by 27 will give you 40 by 27 into 6 by 2, which is 3. So many moles of electrons. And 1 mole of electron is 1 Faraday here. So how much is that? So this is 40 upon 9 Faraday. How much is that? I mean, just divide that. That's not a big deal. I think this is 4.44 Faradays. So 4.44 Faradays of charge is required in the second case. Oh my God, you didn't use the formula. If you want, I can do that again, no problem. So the formula would run like this. W is MIT by NF. W is 40 grams. M is 27 atomic mass of aluminium. IT by F will remain as it is. And N has a value of 3. Why 3? With 1 aluminium, you need 3 electrons. Please remember, whenever you're calculating N, if you're calculating N, I'm giving you a very good tip. Please remember, if you are calculating N for aluminium, then change the coefficient of aluminium to 1. If this becomes 1, with 2 it is 6. If it is 1, this would become 6 divided by 2, which is 3. And that is why we are taking the value of N as 3. If you are trying to calculate N for any species, always in the balanced equation, use 1 mole of that species and see whatever is the number of moles of electrons or whatever is the coefficient of electrons, that is the value of N only for that species. So for aluminium, the value of N is 3. This is how we do this. Got it? Good tip. So IT by F is so much. And how much is that? So therefore, IT by F is 40 by 9, or IT, which is charge, which is 40 by 9 Faraday, which we got there also. Whichever way you love it, do it. How much electricity is required in coulombs for the oxidation of 1 mole of H2O to O2 and 1 mole of FeO to Fe2O3? Let's calculate. How much of electricity? Okay. Now, if H2O is getting oxidized to O2, I'm solving part 1. If H2O is getting oxidized to O2, can I have the equation? Okay. So, this is required. So, for 2 moles, now I need H2O 1 mole. So, if I just change the balancing, I have H2O, it will be half O2 plus 2H plus 2 electrons. So what is the value of N? The value of N is 2. Why? Because I am interested in H2O, and with 1 mole of H2O, the value of the coefficient of electrons is 2. So the value of N is 2 in this case. How much of electricity is required? I mean, that's not very difficult to see. If I take 1 mole of H2O, I get 2 moles of electrons. That means 2 Faradays of electricity is required. In coulombs, well, I can do this in coulombs also. 2 into 96500 approximately or accurately 2 into 96487 coulombs. So whichever suits you, you can take that. I'll go for the accurate answer. So many coulombs would be required for case 1. Simple? Simple. What about the second one? Let's take a look at the second question. Here, second part of the question. 1 mole of FeO to Fe2O3. Now, if FeO, my dear, gets oxidized to Fe2O3, say half a mole or whatever, now, do you see that there is a change? How much change? This plus oxide if you take. So, and that oxide also should be 0.5 oxide ions. What are you doing? Some stupid kind of a balancing. If you don't like 0.5, I could do it as 2 times FeO. I'll change the coefficients to make it look more friendly. FeO is getting oxidized to Fe2O3. It could be like this. This is more helpful? Yes. How did I write this equation? I wrote FeO, I wrote Fe2O3. Now, the only element was, this was half equation. Iron goes from +2 to +3, it is undergoing oxidation. Oxygens I am not changing. So, I had 3 oxide ions here. I had 2 oxide. So, I just added 1 more oxide to first complete the material balance. And then lastly, I added electrons to complete the charge balance. This is what I did. Okay, fine. What is the value of N? Now, I have 1 mole of FeO. If I am considering FeO, if I take 1 mole of FeO, I take 1 mole of electrons. So, 1 mole of electrons, that means 1 Faraday charge. That means 96487 coulombs of charge is required. That is the answer, my dear, for the second part. Simple, beautiful. And there comes a beautiful question based on Faraday's laws of electrolysis. It says, a solution of nickel nitrate is electrolyzed between platinum electrodes using a current of 5 amperes for 20 minutes. What is the mass of nickel deposited at cathode? Now, what is the reaction at cathode? At cathode, you have Ni2 plus undergoing reduction to give you nickel. Right? And as per the formula for Faraday's first law, W is MIT by NF. M is atomic or molecular mass of the substance deposited or dissolved. In the case, Ni is deposited, and atomic mass of nickel we would need here, into current I. Current I is 5 amperes into T. Time is 20 minutes. We need to change that in seconds. So 20 into 60. So many seconds by N. What is the value of N? N is 2. And F, 96487, if you really wish to drag that on. Right? All we need to do is get the value of M, solve it, and get the answer. Nickel is around 58 point something actually, 58.7 if you care, for accuracy that is. If you solve that, you get around 1.825 grams. Wow, that is the mass of nickel deposited? Yes, indeed. The question says, 3 electrolytic cells A, B and C containing solutions of zinc sulfate, silver nitrate and copper sulfate respectively. Oh my God. So I have 3 solutions. I have zinc sulfate, apparently then I have silver nitrate, zinc sulfate, I have silver nitrate, and I have copper sulfate. Fine. And what am I doing? Well, as I set up the reaction, if I pass current in series, do you see that same current will flow through each solution? This is a solution. So the amount of current flowing through these solutions is exactly the same. I am using a battery here. Fine, anything of that kind. These are connected in series. A steady current of 1.5 amperes flows through them. So I is 1.5 amperes. Fast, fanciful. Until 1.4 grams, the mass of silver deposited is 1.45 grams. How long did the current flow? So I am supposed to find out time t. that will be using Faraday's first law. And what would be the mass of copper and zinc deposited? We will use Faraday's second law for this. Let's start. Well, mass of any substance M is, W if you say, is MIT by NF as they call it. The mass of silver deposited 1.45 grams. Atomic mass of silver is 108. Current is 1.5 amperes. Time t we have to calculate. N for silver, Ag plus 1 to 0, and the value is 1 into F, 96487. Very loving calculation. T is 96487 into 1.45 divided by 108 into 1.5 seconds. Let's do that. That gives you 863.6 seconds. If you divide that by 60, that would correspond to around 14.4 minutes. That would be the time for which the current would need to flow in order to deposit barely 1.45 grams of silver. First part. What about the masses of copper and zinc deposited? Faraday's second law says that if same current is passed through different solutions, then the masses of substances liberated or dissolved are in the proportion of their equivalent masses. So, mass of zinc by mass of silver is equivalent weight of zinc by equivalent weight of silver. Now, what is equivalent weight of zinc? Equivalent weight is atomic mass by N, charge. 65.4 is atomic mass for zinc, divided by 2 is equivalent mass of zinc. For silver, it is 108 divided by 1. That's it. Mass of silver is known as 1.45 grams. Therefore, can I calculate the mass of zinc? Easily. Mass of zinc. And this comes out to be 0.429 grams barely. That's pretty less, whatever it is. Could we also do a similar stuff for copper? Of course. Mass of copper by mass of silver, which is 1.45 grams, is equivalent weight of copper by equivalent weight of silver, which is atomic mass of copper by N factor of copper is 2. Atomic mass of silver is 108 and factor is 1. Oh my God. What do? We solve it, of course. And this comes out to be 0.426 grams. This is actually 0.439, not 2. Right? Just ugly calculation, nothing else. This is the way we have it. There comes a very, very interesting question from NCERT. They are talking about feasibility of a reaction using the standard potentials given in table 3.1. That is a table which we have seen earlier, right? This table they are talking about. This classic NCERT table in which electrochemical potentials are mentioned. You have to use this table and determine if the reaction of these combinations is actually feasible. We'll take them one by one and see. How do we do this? Let's start. You'll see. Let's take the first one. Ferric and I minus. Tell me, in case ferric and I minus react, what possibly could they have done? Well, ferric can undergo reduction and it can form ferrous. I minus can undergo oxidation and it can form I2. Oh my God. Is this reaction feasible? We will have to check. How exactly? Delta G naught negative implies feasible. Okay. But delta G naught is minus NF E naught. That should be negative. That means E naught should be positive because N and F are always positive. If I multiply by minus 1, the inequality sign reverses. That means if the reaction has to be feasible, then E naught cell has to be positive. So all I need to do is to calculate E naught cell. But do I know the formula? Of course. E naught cell is E naught cathode minus E naught anode. And in this case, cathode is the one which undergoes reduction, and that is ferric. So this is E naught of ferric to ferrous minus E naught of I2 to I minus. Because this is undergoing oxidation and we are supposed to quote the SRP value of that. If I look in the table 3.1 as they have mentioned, I would discover the values as 0.77 volts minus 0.535 volts. Is this positive? Of course it is positive. If it is positive, that means E naught cell is positive, which means that delta G naught is negative, which means that the reaction is feasible. There we are. It's feasible. Done. Similarly, we can do all three. Yes, the remaining three also can be done with a very similar concept. Every time I will not repeat this, but this is the criteria. Right? Let's do that. Ag plus, the second part now. Ag plus aqueous and copper solid. I mean, how could they react? What would happen? Well, Ag plus would be reduced to Ag and copper would be oxidized to copper ions. Something like this. Oh, wow. Now, E naught cell for this reaction is E naught cathode minus E naught anode. Which is cathode? Which undergoes reduction. And who undergoes reduction? Silver undergoes reduction. So let's take that as cathode. This is E naught of Ag plus to Ag minus E naught of copper to copper ions. Cu2 plus to Cu. You can say this is anode. Fine, but we are writing SRP, so we have to write like this. And because anode, we have put a minus sign. That's a part of our formula. If you check in table 3.1, what do you get? You get Ag plus to Ag is 0.8 volts minus copper ions is 0.34 volts. Is this positive? I'm not even bothering to calculate it. Is it positive? Yes. Is E naught cell positive? Yes. That means this means delta G naught is negative. That means, is it spontaneous? Yes, it is spontaneous. Is it feasible? Yes, this is also feasible. Now let's explore the possibility of the third one. I'm not saying this is feasible, I'm just saying we're talking about third one. Ferric and Br minus, just like ferric and I minus. Ferric is coming so very often actually. So we could do actually third and fourth together. We have ferric with Br minus or silver. Let us see if they are feasible. Let's take a look. See, if ferric ions are treated with maybe Br minus, or if ferric ions are treated with maybe silver, what exactly happens? Ferric may get reduced to what? Of course to ferrous. And what about silver? Silver gets oxidized to Ag plus, or Br minus gets oxidized, of course, to bromine. It's a very, very similar story. E naught cell is E naught cathode. Now, cathode is where reduction occurs, which is ferric ions to ferrous, minus E naught anode. Anode is where oxidation occurs, Br minus to bromine, like this. Do I have the values? From table 3.1, you could look at the values. This is 0.77 volts minus 1.09 volts. Oh my God, this is negative. Yes, it is negative. Is it feasible? No, this is not feasible. Therefore, delta G naught, which is minus NF E naught, is positive. That means this is not feasible. So this was yes, this was yes, this is a no. Oh, what about the fourth one? Very similar. E naught cell is E naught of ferric ions to ferrous minus E naught of Ag plus to Ag. If I look at table 3.1 and discover the values, this is 0.77 volts minus 0.80 volts, which is minus 0.03 volts. Small, but nonetheless negative. It is negative, goddammit. That means it's not feasible. No, it's a no. It's a no. YYNN. And the last, bromine and ferrous intend to react. Now, if bromine intends to react with ferrous, what might they do? Well, bromine would get reduced, Br minus, and ferrous would get oxidized. It would give you ferric. Oh, that's nice. How do I solve this? E0 cell would be E0 cathode. Cathode is the reduction occurs. The E0 of bromine to Br minus. Why? Because this is where reduction is happening. What about cathode? Sorry, anode. Anode is where oxidation occurs. That is the definition. Minus E0 of, this is 1.09 minus 0.77 volts, which is positive, yes. So is this reaction feasible? Yes. And actually, if you care to see, fifth is just reverse of third. If third is non-spontaneous, fifth, because it is just reverse, fifth is bound to be spontaneous, and yes, it is. So the answers are yes, yes, no, no, yes. This is how we do this. And there comes a question based on electrolysis, which says, predict the products of electrolysis in each of the following. 1. An aqueous solution of silver nitrate with silver electrodes. Now, what happens? See, in case 1, at anode, if you have silver electrodes, then silver gets oxidized, preferably as compared to water or anything else. So, new silver, the anodic silver, actually reacts and dissolves in water, forming silver ions. And then what happens at cathode? Now the solution has plenty of silver ions. So silver ions just take up electrons and get deposited. So Ag at anode just gets transferred to Ag at cathode. And nothing new happens when we are talking about electrolysis products, when silver nitrate aqueous solution is electrolyzed using silver electrodes. Beautiful but simple. And you know, this reaction is used very much in electroplating of silver. Say for example, at anode you dip a silver rod, and at cathode you're having a spoon or a plate or a statue. Can spoon or plate or statue function as electrode? Yes, they can. You just have to pass current, that's it. So you would find that silver rod would dissolve at anode, and slowly silver gets deposited at cathode. Maybe it's a spoon. So although the spoon might have been an iron spoon, but as silver gets deposited, it begins to look like a silver spoon. It now becomes a silver coated spoon. Electroplating is a very popular thing which is done using electrolysis like this. Second, an aqueous solution of silver nitrate with platinum electrodes. Oh my God, now this is going to be a mess. Why? In the second part, if you're using platinum electrodes, now platinum is very inert and unreactive. Platinum at anode would not undergo oxidation. Now, since nothing else is there at anode, water will have to undergo oxidation. Poor water, it undergoes oxidation to give you oxygen, to give you electrons, and of course, free H plus ions. And what happens at cathode? Well, at cathode, you have Ag plus ions shamelessly eating away electrons to give you silver. If you add, what do you get? Multiply by 4 in the cathode reaction and add, you get 4 times Ag plus 2H2O, giving you 4 times Ag plus 4 times H plus O2 like this. So what happens? Products of electrolysis, you find at anode, acid, H plus is acid and O2. At anode, O2 and H plus is liberated. At cathode, silver gets deposited. These are the reactions which occur during electrolysis of silver nitrate aqueous using platinum electrodes. The third one says, a dilute solution of sulfuric acid with platinum electrodes. Now this gets very interesting again. Why? Because at anode we have to make some kind of an oxidation, and anode attracts anions. Now, anion which is attracted at anode is sulfate, and sulfate is not any anion which easily undergoes oxidation under normal circumstances. So please leave H2SO4 out. It is water, the poor water, the very reactive, not reactive but very, you can say very brave water which comes to rescue. It says, no, I will undergo oxidation. Water gets oxidized, liberates bubbles of O2 acid and gives away electrons. And what happens? Because we have H plus ions, these H plus ions thanklessly eat away all the electrons, and what you get actually is this. 4 electrons, 4H plus. In order to multiply, add them properly, electrons must cancel. So I should multiply the lower equation by 2, add up. What do I get? Well, interestingly, you will see H plus also cancels away, leaving you the overall electrolysis equation as water, giving you 2 times H2 plus O2. H2 is at cathode and O2 is at anode. So simply water is being electrolyzed, that's it. You get nice and happy O2 and H2 liberated at anode and cathode respectively. This is what which happens if you electrolyze dilute sulfuric acid. Last and the least, we have aqueous solution of copper chloride. If you have copper chloride at anode, first of all you have anion, and anion is chloride ion. Wow! So chloride ion undergoes oxidations and liberates chlorine. Please remember, much of it is chlorine, but chlorine is a difficult gas to liberate. Sometimes as concentration of chloride ion decreases, partly water can also undergo oxidation, liberate O2 and H plus, but that is not a major reaction initially. We can simply write down, we have chloride ions giving you chlorine, and at cathode you have those most loving copper ions which are shamelessly getting reduced to copper. So you have CuCl2 giving you Cu plus Cl2. That's a stupid reaction. Copper chloride as a compound on electrolysis produces, it deposits copper metal at cathode and it liberates bubbles of chlorine gas at anode. That is what which happens. So dear students, this was a fascinating discussion of the most interesting of all and probably the most feared of all chapters, and that was electrochemistry. Not just the solutions have been covered, I repeat, I have also tried to give you insights into various workings of theory. It is full with so many tips, so many tricks, so many concepts that if you actually go through these solutions and discussions, you're bound to find them very useful and very, very enriching. Do comment and write down how you find them. If you like them, of course, press the like button, and don't you forget to share this with your friends and everybody you know about. Subscribe, like and share. Have a great time.